Hello everyone, welcome to my YouTube channel. In previous video, we have discussed first and second shifting theorem for inverse Laplace transform. Further, we have discussed few important examples on first and second shifting theorem for inverse Laplace transform. In this video, we will discuss inverse Laplace transform using the partial fraction technique. In this video, we will discuss three examples. In first example, we will have a function whose denominator contain non-repeated linear factor. In second example, we will have a function whose denominator contain repeated linear factor, and in third examples we will have a function whose denominator contain quadratic factors. These are three basic types of functions in which we use partial fraction technique. So let us see how we use partial fraction technique to find inverse Laplace transform. The first example is find the inverse Laplace transform of 2s square minus 4 upon s plus 1 into s minus 2 into s minus 3. So here the denominator of this function contain non-repeated linear factors, and we have to find its inverse Laplace transform. So let f bar s is 2s square minus 4 upon s plus 1 into s minus 2 into s minus 3. Now we apply partial fraction technique on the function f bar s. So using the partial fraction method, we get 2s square minus 4 upon s plus 1 into s minus 2 into s minus 3 equal to a upon s plus 1 plus b upon s minus 2 plus c upon s minus 3. So this we do the partial fraction with this function whose denominator contain non-repeated linear factors. Now we have to find the values of the constant a, b and c, and for this we multiply this whole expression by s plus 1 into s minus 2 into s minus 3. We get in left hand side we have 2s square minus 4. When we multiply this expression by s plus 1 into s minus 2 into s minus 3, then this whole expression cancel and we have only 2s square minus 4 equal to, in right hand side s plus 1 is cancelled, then we have a into s minus 2 into s minus 3 plus here s minus 2 cancel. When we multiplied s plus 1 s minus 2 s minus 3, we have b into s plus 1 into s minus 3 plus here when we multiply by s plus 1 into s minus 2 into s minus 3, then s minus 3 cancel and we have c into s plus 1 into s minus 2. Now to find the values of a, b and c, first we put s equal to minus 1. Then here minus 1 plus 1 cancel, so this expression is 0. Here minus 1 plus 1 cancel, so this expression is also 0. In left hand side minus 1 square is plus 1 and 1 multiplied by 2 is 2 and 2 minus 4 is minus 2. So in left hand side we have minus 2 and in right hand side s equal to minus 1, so minus 1 minus 2 minus 3 and minus 1 minus 3 minus 4. So minus 3 into minus 4 is plus 12. So we have 12 a's. So minus 2 equal to 12a, then a is equal to minus 1 by 6. So this is the value of a. Now we put s equal to 2 in this expression, then s equal to 2, this expression becomes 0, and s equal to 2 gives this expression 0. In left hand side, when we put s equal to 2, we get 2 square is 4, 4 into 2 8, 8 minus 4 is 4, and in the right hand side we have these two are 0, and we put s equal to 2, then we have 2 plus 1 3, and 2 minus 3 minus 1. So we have minus 3b. So 4 equal to minus 3b, which gives b equal to minus 4 by 3. Now we put s equal to 3, then this expression 0, this expression also 0 when s equal to 3. In left hand side, when we put s equal to 3, we get 9 into 2, 18, 18 minus 4 is 14. And in the right hand side, these two expressions are 0, and here we have 3 plus 1, 4, and 3 minus 2, 1. So we have 4c. So 14 equal to 4c gives c equal to 7 by 2. 14 by 4, which is equal to 7 by 2. So this we find the values of constant a, b and c. Now we put the values of a, b, c in expression 2. That is, in this expression we put the values of constant a, b and c. We get, after putting the values of a, b, c in equation 2, we have 2s square minus 4 upon s plus 1 into s minus 2 into s minus 3 equal to minus 1 by 6, which is the value of a, upon s plus 1, plus minus 4 by 3, which is the value of b, upon s minus 2, plus 7 by 2, which is the value of c, upon s minus 3. So this we complete the partial fraction of the given expression. Now we take inverse Laplace transform on both sides. We get inverse Laplace transform of 2s square minus 4 upon s plus 1 into s minus 2 into s minus 3 equal to inverse Laplace transform of this expression. Here we apply the linear property of inverse Laplace transform. So after applying the linear property, we have this inverse Laplace transform is equal to minus 1 by 6 constant multiple, so as it is, into inverse Laplace transform of 1 upon s plus 1. Here minus 4 by 3 constant, so as it is, in multiple we have minus 4 by 3 into inverse Laplace transform of 1 upon s minus 2, plus here 7 by 2 constant multiple as it is, so plus 7 by 2 into inverse Laplace transform of 1 upon s minus 3. So this is, we apply the linear property. Now as we know, the inverse Laplace transform of 1 upon s minus a is e raised to at. Inverse Laplace transform of 1 upon s minus a is e raised to at. So here we have 1 upon s plus 1. So inverse Laplace transform of 1 upon s minus minus 1 is e raised to minus t. Here 1 upon s minus 2. So inverse Laplace transform of 1 upon s minus 2 is e raised to 2t. And here we have 1 upon s minus 3. So inverse Laplace transform of 1 upon s minus 3 is e raised to 3t. So using the formula that inverse Laplace transform of 1 upon s minus a is e raised to at, we get the inverse Laplace transform of 2s square minus 4 upon s plus 1 into s minus 2 into s minus 3 is minus 1 by 6 constant as it is. Inverse Laplace transform of 1 upon s plus 1 is e raised to minus t. Minus 4 by 3 constant as it is. Inverse Laplace transform of 1 upon s minus 2 is e raised to 2t. Plus 7 by 2 constant as it is. Inverse Laplace transform of 1 upon s minus 3 is e raised to 3t. So this is how we use the partial fraction technique to find the inverse Laplace transform. Next example is find the inverse Laplace transform of 4s plus 5 upon s minus 1 whole square into s plus 2. So here the denominator of this function contain one linear factor s plus 2 and one linear repeated factor s minus 2 whole square, and we have to find its inverse Laplace transform. So let f bar s is 4s plus 5 upon s minus 1 whole square into s plus 2. Now we apply partial fraction technique. We get 4s plus 5 upon s minus 1 whole square into s plus 2 is equal to, the partial fraction of this expression is a upon s minus 1 plus b upon s minus 1 whole square, because s minus 1 whole square is linear repeated factor, plus c upon s plus 2. So this is the partial fraction of given expression. Now we have to find the values of constants a, b and c, and for that we multiply this equation, whole equation, by s minus 2 whole square into s plus 2. So after multiplication we get the left hand side become 4s plus 5. When we multiply the left hand side by s minus 1 whole square into s plus 2, then this LCM, this denominator is cancelled with the multiple factor, and we have 4s plus 5 only in left hand side. Now in right hand side, each term we multiplied by s minus 2 whole square into s plus 2. Then in this expression, s minus 1 cancel with 1 power of s minus 1, and we have a into s minus 1 into s plus 2. Plus here s minus 1 whole square is cancelled with s minus 1 whole square, and we get b into s plus 2. Plus when we multiply c upon s plus 2 by s minus 1 whole square into s plus 2, then s plus 2 cancel, and we get c into s minus 1 whole square. Now to find the values of a, b and c, first we apply substitution technique. We put s equal to 1, then this expression becomes 0 and this expression becomes 0. In left hand side we get, when s equal to 1, we get 4 into 1 is 4, 4 plus 5 is 9, and here in right hand side we get 3b for s equal to 1. So put s equal to 1, we get 9 equal to 3b, which gives b equal to 3. Now we put s equal to minus 2, then this expression at s equal to minus 2 becomes 0, and this expression becomes 0, and this expression is minus 2 minus 1 is minus 3, and minus 3 whole square is 9. So in right hand side we get 9c, and in left hand side when we put s equal to minus 2, we get minus 8 plus 5 is equal to minus 3. So put s equal to minus 2, we get minus 3 equal to 9c, which gives c equal to minus 1 by 3. Now we have to find the value of a, and we cannot use the substitution technique to find the value of a. So we use comparison method. We compare both sides of this expression, equation third, coefficient of s square. We compare the coefficient of s square in both sides of equation third. So here we have s square into a, so coefficient is a, and further from this term we have cs square. So the coefficient of s square in right hand side is a plus c, and in left hand side there is no s square, so the coefficient of s square in left hand side is 0. So comparing the coefficient of s square in both sides of equation third, we get 0 equal to a plus c, which gives a equal to minus c and become a equal to plus 1 by 3, as the value of c is minus 1 by 3. So these are the values of a, b, c. Now we substitute the values of a, b, c in equation second. We get 4s plus 5 upon s minus 1 whole square into s plus 2 is equal to a upon s minus 1, and the value of a is 1 by 3, plus b upon s minus 1 whole square, and the value of b is 3, plus c upon s plus 2, and the value of c is minus 1 by 3. So this we complete the partial fraction of given function. Now we take inverse Laplace transform in both sides. We get inverse Laplace transform of 4s plus 5 upon s minus 1 whole square into s plus 2 is equal to inverse Laplace transform of this partial fraction. Here we apply linear property of inverse Laplace transform, which gives inverse Laplace transform of given expression equal to 1 by 3 constant, so as it is in multiple term, into inverse Laplace transform of 1 upon s minus 1, plus here 3 is constant, so as it is 3 constant multiple, into inverse Laplace transform of 1 upon s minus 1 whole square, plus here minus 1 by 3 constant, so as it is in multiple term, we get minus 1 by 3 into inverse Laplace transform of 1 upon s plus 2. Now using the formula that inverse Laplace transform of 1 upon s minus a is e raised to at, we get inverse Laplace transform of 1 upon s minus 1 is e raised to 1t, that is e raised to t. So we get 1 by 3 e raised to t. Now in this term we have 1 upon s plus 2, which is 1 upon s minus of 2. So using this formula 1 upon inverse Laplace of 1 upon s minus a is e raised to at, we get the inverse Laplace transform of 1 upon s plus 2 is e raised to minus 2t, as the value of a is minus 2. Now this is the function of s minus 1, f bar s minus 1, because of whole square. So this expression is inverse Laplace transform of function of s minus 1, and we use the first shifting theorem of inverse Laplace transform, that the inverse Laplace transform of f bar s minus a is e raised to at into inverse Laplace transform of remaining expression, that is f bar s. This a goes in the exponential term into inverse Laplace transform of remaining expression, that is f bar s. So to find inverse Laplace transform of this term, we use first shifting theorem. This gives 3 as it is. This 1 goes in the exponential term, we get e raised to 1t into inverse Laplace transform of remaining expression, and remaining expression is what? 1 upon s square. So here we apply the first shifting theorem. Now as we know, the inverse Laplace transform of t is 1 by s square. Therefore inverse Laplace transform of 1 by s square is t. So finally we get the inverse Laplace transform of given expression is 1 by 3 e raised to t plus 3 into e raised to t into t, the inverse Laplace transform of 1 by s square, minus 1 by 3 e raised to minus 2t. So this is how we use partial fraction technique to find inverse Laplace transform when the denominator of given function contain repeated linear factor. Next example is find the inverse Laplace transform of 2s square minus 1 upon s square plus 1 into s square plus 4. So here the denominator of given function contain two quadratic factors and we have to find its inverse Laplace transform. So let f bar s is 2s square minus 1 upon s square plus 1 into s square plus 4. Now we apply the technique of partial fraction on the function f bar s. We get the partial fraction of 2s square minus 1 upon s square plus 1 into s square plus 4 equal to as plus b upon s square plus 1, because s square plus 1 is quadratic factor. So in numerator we have two constant a and b plus cs plus d upon s square plus 4. Again s square plus 4 is quadratic factor, so we have two constant in numerator. Now to find the values of constant a, b, c and d, we multiply this whole expression by s square plus 1 into s square plus 4. Then in left hand side, when we multiplied by s square plus 1 into s square plus 4, so this denominator cancel with the multiple factor and we have 2s square minus 1 only in the left hand side, equal to, in right hand side, when we multiply this expression by s square plus 1 into s square plus 4, then s square plus 1 s square plus 1 cancel and we get as plus b multiplied by s square plus 4. Now when we multiply this expression by s square plus 1 into s square plus 4, then s square plus 4 s square plus 4 cancel and we get cs plus d into s square plus 1. Now here the method of substitution is a little bit complicated, so we use method of comparison to find the values of constant a, b, c and d. So first we compare the coefficient of s cube, and since in left hand side there is no s cube term, so the coefficient of s cube in left hand side is 0, equal to, in right hand side the coefficient of s cube is here as cube, so coefficient is a, and from here we have cs cube, so plus c. So in right hand side the coefficient of s cube is a plus c, and in left hand side the coefficient of s cube is 0, so 0 equal to a plus c. Now we compare the coefficient of s square. So in left hand side the coefficient of s square is 2, which is equal to the coefficient of s square in right hand side. And in right hand side, when we multiply these two terms, we get bs square. So coefficient of s square is b, and from here we have ds square. So the coefficient of s square in the right hand side is b plus d. Now we compare the coefficient of s. So in the left hand side there is no s, so coefficient of s is 0, and in the right hand side the coefficient of s is 4as. So the coefficient is 4a, plus from here we have the term cs. So the coefficient of s is c. So we have 0 equal to 4a plus c. And finally we compare the constant term, that is the coefficient of s power 0. And the constant term in the left hand side, the constant term is -1. The term which not contain s is -1. And in right hand side, the constant term is 4b, which not contain s, plus here the constant term is d. So we have -1 equal to 4b plus d. So we get 4 relation to identify 4 constant. Now using these two relation of a and c, when we subtract these two relation, we get 3a equal to 0, and which give a equal to 0. And when we put a equal to 0 here, we get c equal to 0. So these two equation gives a and c are 0. Further we simplify these two equation, we subtract these two equation, then we get -3b minus 3 equal to 3b, which gives b equal to -1. And when we put b equal to -1 here, we get d equal to 3. So we get the values of constant a, b, c and d. Now putting the values of a, b, c, d constant in equation 2, we get the partial fraction of given expression is 2s square minus 1 upon s square plus 4 into s square plus 1 equal to a is 0 and b is -1. So we get -1 upon s square plus 1 plus cs plus d. So c is 0 and the value of d is 3. So we get 3 upon s square plus 4. So this we complete the partial fraction of given function. Now we take inverse Laplace transform in both sides. Then we get the inverse Laplace transform of 2s square minus 1 upon s square plus 1 into s square plus 4 equal to inverse Laplace transform of -1 upon s square plus 1 plus 3 upon s square plus 4. Here we apply linear property of inverse Laplace transform, and then we get minus is constant, so we write outside, and we get inverse Laplace transform of 1 upon s square plus 1 plus here 3 is constant, so we write outside, and we get inverse Laplace transform of 1 upon s square plus 4. So numerator is constant. So as we know, this numerator constant is such a way that its square appear in denominator here. So this is 2 square, so we require 2 here, so we multiply and divide by 2. So we get 3 by 2 into inverse Laplace transform of 2 upon s square plus 4. Now as we know, the inverse Laplace transform of a upon s square plus a square is sin 80. Therefore the inverse Laplace transform of 1 upon s square plus 1 square is sin 1t. So we get minus sin t plus 3 by 2 inverse Laplace transform of 2 upon s square plus 2 square is sin 2t. So this is the inverse Laplace transform of given function, and this is how we use the partial fraction technique to find the inverse Laplace transform of a function whose denominator contain quadratic factors. In next video, we will take few important questions which are frequently repeated in various university examinations. So see you in next video. Thank you.